find out whether
I
it's
know
an
what you're
impossible
saying.
index.
Just
And that's
like
how I
if you
find out that the
move
7.
one value and
The 7. That's how I found out that the 7 cannot possibly be.
Okay. Welcome to Hopf Algebras. Maybe this is not the best welcome, but actually I was sitting in a graduate class yesterday, and this freshman walked in, and you know they asked everybody to introduce themselves, and he said, "Oh, I'm a freshman, and this is my friend who's with me," and it was pretty clear that the class was not for him, just from what he was writing on the piece of paper. So I thought at least once you see this, there's probably no freshmen left in this class. Right? Anyway, so this is Hopf Algebras. This is a Hopf algebra. Now, what are we going to make with this, right? So basically, it's going to take us a little while to understand what a Hopf algebra is. I want you to see it, but it's just so you see kind of where we're headed one day. But what we're going to do is make things very concrete, very, very tangible, and work our way towards understanding what this is all about. Okay, so I know when you see this, there's probably two kinds of mathematicians. There's a kind of mathematician that goes in, looks at this, and gets really excited and wants to know more about it. And there's another kind of mathematician that walks in, sees this, and wants to leave. I hope nobody has left yet. I will tell you that I'm actually not sure which kind of mathematician I am. Maybe I am. Sometimes I'm the first kind. Sometimes I'm the second kind. And so what we're going to do is a gentle introduction to Hopf algebras, which will include abstraction like this, and it'll also include very concrete computations and very concrete examples and all of that. Okay.
Excuse me.
Yep.
Can you say just one sentence about application and what main area would it be used?
So let me tell you what I'm going to do today. So I just wanted to start by giving you kind of a quick run through the logistics of the course, and then I'll say a little bit about the history and the motivation behind Hopf algebras, and then we'll get to work. Okay. So let's first talk about the logistics. Okay. So maybe the first thing that I should mention is that the course website is already made. So it's this one, math.sfsu.edu/Federico/Hopf.html. Okay. And in there, you are going to find, among other things, the course syllabus, and I'm just going to go down the course syllabus right now. So maybe the first thing I will say, I know most of you, but not all of you. So my name is Federico Ardila. I am a professor in the math department. This is how you spell my name, and this is how I prefer to be called. You don't need to call me Professor Ardila or Dr. Ardila. If you want to, that's fine, but I prefer Federico. My email is federico@sfsu.edu, and my office is Thornton Hall 927. Okay. Okay. The first thing you'll realize is that I'm wearing a microphone, and that you all heard this audio recording saying, "Is the camera on?" All of this stuff. So I wanted to explain that this course is actually part of this initiative called the San Francisco State Columbia Combinatorics Initiative, and this is a collaboration between San Francisco and Columbia. It's a research collaboration and a training collaboration. Okay, so this class is actually offered simultaneously here in San Francisco and also in Bogota at the Universidad de los Andes. So the lectures are mostly going to be taught here, and they're going to be broadcast over there. And the idea is that I'm going to do everything possible so that you guys over here and you guys over there feel like you are in the same class. Okay. So in particular, one thing that I'm going to do is I'm going to ask you to make a little kind of write-up to explain who you are, and so that you can kind of see each other. And I'm going to set up an online discussion forum so that you are able to discuss the mathematical aspects between the students in San Francisco, the students in Bogota, and there's actually other students that are going to be joining the class. And I'm sorry to single you out, Chetak, but for example, Chetak is a student at UC Berkeley, and there's going to be other students from other universities joining us, and so there'll be an online component to help you kind of work together. Okay. A little bit about the logistics. So this class is going to be based on a couple of things. So there's going to be the lectures, homework. During the first half of the class, you're going to have homework every 2 weeks. It's going to be very interesting homework. You can expect that the homework will range from what you would call exercises, kind of making sure that you understand the definitions and doing some fairly simple computations, to hard problems. And let's be honest about it. Anybody that has taken a class with me knows that I believe in hard work in order to learn a lot. And so the idea of the homework is that I want you to learn a lot. I expect you to work together. I think that's the best way to understand this material. And so you are very much encouraged to work together in the homework, work with the students in the other location, discuss electronically the homework, whatever. Just make sure that you write it on your own. Okay. So that'll be the first half of the class. It's going to be 5 homeworks, once every 2 weeks. And then in the second half of the class, you're going to do a project. And the idea of that is to give you a little bit of a taste of what research in mathematics looks like, because I know many of you are thinking of devoting yourselves to that. And so maybe it's good to get a little taste of it before you go into it. And hopefully I can convince you that this is really fun. And or I can help convince you that this is really fun and that you should do it. So you're going to do a project. You're going to do it in groups of 2 students per group. If there is an odd number of students, we'll have to think of something. The idea of the project is that you can do one of many things. So for example, you can choose an aspect of the class that interests you and just go deeper into it and learn a little bit more about it. Or you can understand what an open problem is on the field. I'm going to give you several questions that nobody knows how to solve, and you can just look at one and see what it is that people are trying to solve, and maybe even think about how you might get started. Or if you want, you can solve an open problem, and then that would be great. And I should say that I've done these kinds of classes 4 times before, and I have seen the 3 kinds of projects, and I'm very happy with all 3 kinds. Okay. I'm going to give you an encouragement to do the project between a person in San Francisco and a person in Colombia. Okay. Well, as you can see, the class will be taught in English, so you guys are lucky. You guys over there are also lucky because you get to practice your English. And if anybody wants to write their assignments in Spanish, that is fine too. Whatever you're more comfortable with. I mean, I know there's Spanish speakers in San Francisco also, and if you guys want to practice your Spanish, I'm happy with that too. Textbook. There is no textbook, and I will explain why. But basically what happens is that the kind of class that I want to teach, there is not a textbook for, I think. There's not a textbook that does what I want to do. And if you come to my office, you'll see the 15 different books that I'm looking at, trying to put together a class that tells the story that I want to tell you. And so what I'm going to do is then I'm going to publish lecture notes while we go on in the class. And I'll give you, as we're going through certain things, like I'm going to tell you where you can read more about them. In the syllabus, you're going to find the 3 main sources. And there's going to be a bunch more that we will be, I'll tell you when we're doing something that is not in these sources, yeah?
But we're going to be able to get those for free, the 3 sources, or your lecture
I'm going to make the lecture notes available for free. I'm not sure about the books. And to be honest, I don't necessarily recommend buying them. I mean, it never hurts to buy a book, but I think you'll find that I'm really not going to stick too closely to any one of the books. So it'll be a good supplement, but it won't be necessary to follow the class. We're going to do office hours, but I think maybe we're going to do democratically a choice of what the best office hours are. But I think maybe let's do the math first, and then when we turn off the camera, we can do that. So please remind me maybe 5 minutes before the class is over to discuss when office hours should be. And prerequisites, you should have taken either Math 435 or 735, Algebra 1, in Los Andes, Álgebra Abstracta 2, or something equivalent. So if you don't satisfy those requirements, then please talk to me, and we'll decide if it's a good idea for you to take the class or not. And you can see the grading percentages and everything on the syllabus. But that's basically it as far as logistics are concerned. Okay. Any logistical questions before we go on? Okay. So let's talk a little bit about Hopf Algebras. First, let me tell you just very, very roughly about the history of Hopf Algebras. So Hopf was a topologist in the 40s, German topologist. The theory of Hopf Algebras was born in the study of algebraic topology. I don't think that Hopf actually wrote down the definition of what is now called a Hopf algebra, but through the years, people saw that the essence of this was in his work back then. And so that was kind of the birth of Hopf algebras in the maybe mid-40s in algebraic topology. Now, over the years, algebraists kind of got excited about the algebra that was appearing in this topological study, and they started studying Hopf algebras from an algebraic point of view. Yeah, question?
Yeah, so this whole time I heard the word algebra. Now you're saying algebras. What does that mean?
It's a great question. So, for example, even though you've taken several courses called algebra, you don't know what an algebra is. And I will tell you what an algebra is. But if you don't yet know what an algebra is, that's absolutely fine, and I think most of you don't. And I will tell you either today or Thursday. Yeah. So algebra is going to be an object with certain algebraic structure. The kind of algebraic structure that Hopf and his peers discovered inside these topological spaces. So algebraists kind of got excited and took the theory of Hopf algebras and studied it from the point of view of an algebraist. That happened in the 60s, and it still goes on, and there's a lot of interesting kind of algebraic study of this stuff. Then in the late 70s, combinatorialists came on board, and this was largely due to the observations of Giancarlo Rota, who realized that a lot of combinatorial objects have the structure of a Hopf algebra, and that this very powerful machinery that had been developed could be applied to combinatorial questions. And so this was kind of a two-way avenue where combinatorics gave a source of examples of Hopf algebras, and Hopf algebras could be used to prove combinatorial theorems. And then people are really excited about Hopf algebras lately because they started to appear in quantum mechanics. And that's something that I can tell you less about. But beginning in the mid-90s, it's been recognized that Hopf algebras play an important role in quantum field theory. I don't know the first thing about quantum field theory, but if some of you do, then I would encourage you to do your project on this. I think that's a pretty exciting topic. Okay? So that gives you a little bit of a kind of a history of what where Hopf algebras came from, and we'll see what we can do with them. Okay? Let me very briefly just run through this.
Federico,
Yeah.
it sounds like what you said in terms of applications of the Hopf algebra is and it's used on mathematics.
We will see many applications of Hopf algebras. By the way, let me give away my bias. I learned Hopf algebras from Giancarlo Roda, who I just mentioned. I think many of you know that I am a combinatorialist. That's what my research is about, and I like algebra, but algebra I like it as a tool, and so my bias, which will be present in this class, is that I'm interested in applying heavy machinery towards concrete results. And so we will see many applications of Hopf algebra to combinatorics and to other things. That's kind of the short answer. But I think I don't want to say too many abstract things. I want to actually go to concrete examples, and then we'll see what we're actually talking about. Okay. So what is a Hopf algebra? A Hopf algebra is something with a lot of structure. So it's a vector space over a field K. I'm going to give you maybe a 1-minute definition of a Hopf algebra, and then we'll really get into the details later on in the class. So it's a vector space, okay? We're familiar with vector spaces, but there's a lot of additional structure, okay? But basically, the key things are that you need to have a multiplication. In algebra, you have to be careful where you put your arrows. So I shouldn't draw an arrow here. Multiplication. Okay, so you take two elements of H, and you can multiply them and get another element of H. And you have a co-multiplication, which is a little bit stranger, and maybe you're less used to it. And it's kind of the opposite procedure, where given one element of H, it kind of splits into pairs of elements. Okay. So you need a vector space, you need a multiplication, you need a co-multiplication. You need these other two maps that we'll get into later. And I didn't write it, you need also a map from H to H, which is called an antipode. Okay?
So does this multiplication map reverse the co-multiplication map, or is this a different?
I'll get into details later, but for now I just want to give you kind of this is going to be like an impressionist painting. I just want to give you an impression what this is about, and I'll go into the details because we're going to get bored if I go into the details so quickly without seeing examples. I just want to tell you, you can think of a Hopf algebra as a vector space that has a rule for multiplying elements, a rule for co-multiplying elements, whatever that means, you'll see what that means, and an antipode, and you'll see what that means also. So you need all this additional structure, and these multiplication, co-multiplication, and antipode need to satisfy a bunch of properties. This, you probably don't recognize it like this, but this is called the associative property. You probably can't see it, right? We'll see how what I wrote in blue is the associative property. And what I wrote in red is what's called the co-associative property.
So what is the circle with the cross inside?
This is called a tensor product. We haven't seen it. We will see it.
But the one in red, I mean those arrows, delta cross.
Every time you see a little circle with an x inside it, that's called a tensor product, and that's something else that we will define, and I haven't defined it yet.
Operation is defined in the tensor product form?
Yeah. Again, I'll get into specifics later. Bear with me for a moment to give you just a very rough idea. Okay. So this is called the associative law and the co-associative law. You've never seen it look like this, but we will see how the blue thing is exactly what we're used to calling the associative law, and the red thing is some co-version of that. The blue thing here is called the unitary property, and the red thing is called a co-unitary property. And I guess I should have said that this is called the unit, and this is called the co-unit. Okay? And this is a rule that the antipode has to satisfy. Okay? Antipode. in summary, a Hopf algebra is a vector space that has a lot of algebraic structure subject to a lot of rules. Okay, it's a very restrictive object. And because it's such a restrictive object, that means that you can say a lot of things about it. If you put a lot of rules on something, then that something has less room to move around and be different from everybody else. And if we put a lot of rules and force somebody to be a Hopf algebra, then we're going to force it to have a lot of properties. Okay? That's very roughly, in a nutshell, the theory of Hopf algebras. Before I go on, I want to read you a quote that I like a lot. Okay? And this is a quote from a paper of Figueroa and Gracia-Bond. The paper is called Combinatorial Hopf Algebras in Quantum Field Theory. And the quote says, and the quote is relevant to this course, okay? It says, "We do not want to assume that the readership is familiar with Hopf algebra theory, and some find a direct passage to the starchy algebraic diet too abrupt. This is why we start with a motivational discussion." Okay? So the key thing is that you're not alone. If you find a direct passage to the starchy algebraic diet too abrupt. Okay. By the way, every now and then I'm going to have to translate words to Spanish. So starchy means a couple of things. It means almidonado, or it means acartonado. Okay. So they're referring to this as a kind of a starchy diet. So a starchy diet is a diet kind of high in carbohydrates, right? You eat a lot of things, they're very heavy, and it's kind of hard to get through all this food. Okay, so that's what they talk about when they're talking about this. I like the word starchy in English because it refers to the diet, but it also refers to being kind of stiff. And as I told you, we're imposing a lot of structure here, and this is making the objects kind of stiff, okay? And I like that quote a lot. I actually wrote it down in the notes so that you can kind of keep it in mind. We will come up with the tools to ingest this delicious but starchy food. Okay. I think this is especially relevant in Colombia because I've never seen anybody with a more starchy diet than Colombia. It's the only place where you can order an executive lunch, and the executive lunch is a piece of meat, rice, pasta, and potatoes. That's a pretty standard thing that you get. And it's kind of like this, right? Here's your, the extra space is like maybe the meat, and then you have like your rice, your pasta, and your potatoes. It's heavy. But hopefully it'll be worth it, okay? Okay. So that's all that I want to say about generalities. And before defining any of this, because I know there's a lot here, I just want to talk about some motivating examples. Because before I make you learn about this stuff, I need to give you a reason to learn it. Right? They say that you should never learn a theory that doesn't have more than 2 examples. And this is a theory that has many, many examples. Okay, so after all my hard work, I'm going to erase this. Speaking of starchy, has anybody read Gabriel Garcia Marquez? Yeah? Have you? So Gabriel Garcia Marquez, if you don't know, he's like the most famous Colombian novelist, Nobel Prize winner in the early 80s. But I don't know if any of you noticed that every single book he uses the word starchy. And you should just Google Garcia Marquez and starchy. And you'll see. And that's another reason why I like this word. So he always, whenever he's describing a new character, if there's a character that is kind of like it's either like a military person or like a strict school teacher or like a government official, he always describes them in the morning. They get up, and they get up their really, really starchy shirt, and then they go out and take a walk. Okay? And I think it's a good it's a kind of a good mental picture for all of this. Okay. So let's talk about some motivating examples. So that you hopefully can get a little bit more excited about this stuff. So in other words, what I'm going to do is build Hopf algebras from a bunch of things. Groups, polynomial rings, graphs, permutations, etc. Okay? So we're going to see that Hopf algebras give you a common context in which you can study all of these things that seem very different from each other. So I told you that to build a Hopf algebra, you need a vector space. And the key things here are the multiplication and the co-multiplication. Okay? And so for now, I just want to focus on those two, and then we'll see the other stuff later on. Okay? But for each one of these motivating examples, I need to give you a vector space, I need to give you a rule for multiplying, and I need to give you a rule for co-multiplying. Okay? Now, the first problem with this is that you don't know what this means, maybe. Maybe you do, maybe you don't. And so we need to understand what this symbol means, and that's called a tensor product. Okay? So let's talk about that. So this thing is called a tensor product. Okay. If you're planning on turning in your homework on LaTeX, you're going to need to know /O times. Tensor product. So let's say that. I'm sorry? And yeah, if you're planning to type up your homework in LaTeX, you're going to learn a lot of LaTeX in this class, which is great. Because to draw diagrams like what I drew earlier, it's kind of painful, and then when you're done, it's really satisfying. But yeah, so there's /big O times, and that's if you want it to be bigger. Okay, so what is the tensor product? The tensor product is so let's do it for let's take the tensor product of two vector spaces. Just as a first example. So let's say that you have two vector spaces, U and V. So vector spaces over some field K. Okay. If you're not used to this funny K, this is what I usually use to denote a field. Okay. And so whenever you see this K with a little thing behind it, that's going to be a field. Okay. Now the idea is you have two vector spaces, and you want to kind of make them interact with each other. Okay. And there's one way to do this that you have seen before, which is to take the direct product, U times V. Okay. So that's not what this is. So U times V is, what is it? Let's review it. What is U times V?
And the operations would be combinatorics.
Can you add two things like this?
Yeah.
if you add uv and u prime v prime, what is their sum? U plus u prime, v plus v prime. Right? Okay, so let me ask you something. What is the dimension of, let's say that the dimensions of u and v are finite.
The product of the two dimensions.
Is it the product of the dimensions? Is it the sum of the dimensions? This is going to be a nice exercise for you to review your linear algebra. It's the sum, actually. Which is a little bit unfortunate, right? Because we're calling this a direct product, and yet the dimension of the product is the sum. Okay? But you might remember that actually u times v is also sometimes called u direct sum v. And then, okay? And so what we want to do now, and one thing about this is that you're in the direct product, you kind of have u over here and v over here, and they're really not interacting, right? Because we're doing everything component-wise, so u is over here and you're adding things in u, and v is over here and you're adding things in v, and they're not really mixing, okay? And we want to actually make them mix, and that's what the tensor product is for. And so what we do is we're going to build something, and we're going to find that its dimension is going to be the product. Okay. And the idea is going to be that we're going to allow ourselves to multiply elements of u and elements of v, which isn't supposed to make sense, right? Because u is a vector space, v is a vector space, and you don't have any rule that allows you to multiply them, but we're just going to introduce a multiplication. Okay? And so what we're going to do is the following thing. We're going to consider u times v is, so we're going to begin And so what we're going to do is we're going to say, well, maybe I don't know how to multiply elements of u and elements of v. I'm just going to make up a multiplication, okay? And I'm going to define a new symbol, u tensor v, which you think of as the multiplication of u and v. That doesn't actually mean you're multiplying them, but it's just going to be a symbol that denotes the formal multiplication. Yeah?
Are you implying that so u tensor product v is not equal to v tensor product u then? Are they the same?
It's a good question. We'll see. So the question is u tensor v the same as v tensor u? It's a good question. Let me continue, and while we do that, let's think about that, and then I'll let you guys answer that question. Okay. So we're thinking of this as some kind of multiplication, some kind of formal multiplication between u and v. But we would like multiplication to satisfy some rules if we're actually going to call it a multiplication. So what rules do multiplications tend to satisfy? The associative law. Now, what does the associative law mean? The associative law says that when you multiply three things, A, B, and C, it doesn't matter what order you multiply them in. You can do A, B, C, or A, B, C. What is that in this context? So u times v equals v times u is what we would call the commutative law, right? And we actually, we've seen in algebra that you don't want to force things to be commutative if you don't have to, and I'm not going to assume the commutative law. The associative law, u times v times w, should be the same no matter how you parenthesize it. Now, the thing is that there's no w, right? We're just multiplying pairs, and so there's not going to be an associative law here either. What other properties does multiplication satisfy? Multiplication satisfies the distributive law. Okay. U times v plus v prime is u times v plus u times v prime. That actually makes sense here, and I want to impose that relation. Modulo the relations I want to impose that if I do this, it should be the same as if I do this.
Sure, but how do you add the things on the right-hand side?
So let's make sure that everything here makes sense. As soon as you write an expression like this, you have to make sure that everything makes sense. So where does the left-hand side live? Does the left-hand side make sense?
Yes, less than you.
So U lives in capital U. V and V prime live in capital V. Can I add them?
Yeah.
I add them because V is a vector space. Okay, so this makes sense. And so if this is in U and this is in V, then this tensor makes sense. And I'm saying that it should be this plus this. Now this makes sense, right? This lives in U times V. This lives in U times V. What does it mean to do this plus this? Well, this is the span of this stuff. It's like a formal. So far, I've defined this to be the formal, all finite combinations of things like this. And so this is a finite combination of two symbols of this form. So it lives in U. It lives in here. Okay. And so I'm going to impose this relation. Naturally, I should also impose the other relation. So the same relation. On the other side. Yep.
So you said modulo, that's that modulo in the traditional sense of the word.
So modulo, like in the previous algebra class, we're taking this vector space and we're taking modulo. I mean, it's linear algebra. You know. We're taking a vector space modulo a subspace. The subspace spanned by these things. Are there any other relations that I should be introducing here? Yeah.
Should the order be switched on the last one you wrote?
Here and here.
Okay.
I think it shouldn't be, because if you do A plus B times C, then it should be U. I mean, U plus V prime times B should be U times V and U prime times B. Yep. So the other thing we have with vector spaces, you can add things in a vector space and you can multiply them by scalars. Okay, and it makes sense that if I multiply by a scalar on the left-hand side, that should be the same as pulling that scalar out and multiplying by this tensor. Or it should be the same thing as putting the scalar on the other side. So somehow multiplying by scalars, you can do it on the left side, on the right-hand side, or outside, and you should get the same thing. Yeah?
So stepping aside from like operations and symbols and everything, I'm trying to think of how are we supposed to understand the tensor product in comparison to like U cross V? Because you know how you were saying earlier, we did U cross V. We're just doing operations and U vector space operations with these vector space, and then we just slap them together.
Mm-hmm.
Here, the tensor product, are we also just putting things together, or are we living somewhere else? Are we landing somewhere else when we do tensor product?
I think the best way to answer your question is to just give you a concrete example of a tensor product, and we'll see how to multiply in there. Okay. I think I'm going to do an example in a second, and I think that will answer your question, and let me know if it doesn't. Okay. Okay. So this is the tensor product. That's it. You consider all the formal sums of U tensor V, okay, except that you take the modulo of these relations where you have the distributive law on both sides, and you have multiplication by scalars. Okay? That is the tensor product. Yep? So, and I think this is more or less the same question that Krista had. Like, how do you add two tensors? What does it mean to do u tensor v plus u prime tensor v prime. Do we do it component-wise? No, we don't actually. What we do is we just say, well, u tensor v plus u prime tensor v prime is a combination of these things. And so it's nothing but this plus this. It's a formal sum of the first one and the second, as in second. Okay? The only operations you're allowed to do with tensors are these ones. Okay? Let me give you an exercise that I think will help you understand this. Okay. I mean, this is kind of this is the abstract point of view, but maybe you prefer things with coordinates. Maybe it's easier for you to think of vector spaces as r to the n. And so you should think that r to the n tensor r to the m is going to be r to the mn. Okay, and more general, let me just say that if you have a basis this is a basis for u, and this is a basis for v. If these are bases for u and v, then if you consider these things, where I is in I and j is in j, these are going to be, this is a basis for the tensor product. Okay? And so that means that if U has a basis U1, U2, and V has a basis V1, V2, V3, then you can think of the elements in U as being column vectors of length 2. The elements of V are row vectors of length 3. And the elements of U tensor V are just matrices of 2 by 3. Okay.
Can I please make a little request? Whenever you have U and V put together, can you please put a little tail for U?
I should have used V and W, huh? Yeah, I apologize. Let's try to do V and W from now on instead of U and V. Let's do a more concrete example, and I think this will be clearer when I do that. Let's say that U is the real polynomials in the variable x, and V is the, I don't know, let's say the 2 by 2 matrices. Okay. When I write this, I mean every single 2 by 2 matrix with entries in the reals. Okay. So both of these things are vector spaces over R. Okay. What dimension is this one? And let me follow my what I said I was going to do. So let's call this V. Let's call this W. So the dimension of W is 4, right? Because you have 4 degrees of freedom to choose your 4 entries of your 2 by 2 matrix. What about the dimension of U? It's countably infinite. A basis for this is the polynomial 1, the polynomial x, the polynomial x squared, x cubed, and so on. So this is infinite dimensional. This is 4 dimensional. I don't have a rule to multiply a polynomial times a matrix, but I'm just going to introduce one. Okay. So in the tensor product, I can decide to take an element in U, an element in V, such as 2 plus 2x, and tensor it with the matrix 0, 1, minus 1, 0. Okay? that is an element of V tensor W. Now, I'm not saying that I'm giving you any prescribed rule to multiply these things. This is just a formal expression, an element of the first thing, tensor an element of the second thing. But you're allowed to do operations here. So can you think of any operations that I can do to this?
Yeah, we can distribute, and we can pull scalars.
So for example, we could distribute. So if I distribute using this distributive law, I could write this as 2 tensor this plus 2x tensor this. Okay? And this is, this is a sum of tensors, and it happens to equal this. Are there any other things that you see that I can do?
Pull the scalar.
Pull the scalar. So what do you mean by that?
Factor out 2.
For example, I could factor out the 2, and for example, I could take a 2 out of this side and bring it into the matrix. Because I can take a scalar from one side and send it to the other side. So I could do 1 tensor 0, 2, minus 2, 0. Now, I can take this scalar and do this. Yeah? Okay, so you see why I have my red marker. This is something I shouldn't have done. Why can I not do this?
X is on the field basis vector.
Because I can only take scalars out of here and put them into here. But 2x is not a scalar. Right? The scalars are the things in the field. We're considering these as vector spaces over the reals, and so I can only pull out reals. So I cannot pull out 2x, but what could I do? I could pull out the 2, but not the x. Okay? So maybe this is, let me not erase it, let me just tell you this is not something you should do. Don't do this. Okay? But what you can do is this. 1 times this plus x times this. 0, 2, minus 2, 0. Okay? So these are the kinds of operations that you do. Is that a little bit more helpful as far as how you actually work with these tensor products? Okay. Any questions about what I did here? Is there something else that you're tempted to do to simplify this? And if so, let's discuss whether it's legal or not.
Get the 2 outside and then have those 2 things adding inside, like 1 plus x tensor products the matrix.
We can do that.
So I'm hearing you do 2 different things, and they're both valid, at least the 2 that I heard. One is that you can now factor. Because you have the same thing on the right-hand side, you can factor like this. That's fine, right? Here I'm using the distributive law.
Pull out the 2, right? Yeah.
Or another thing that you could do is pull out the 2, and now, so let's pull out the 2 from this side. But now let's not put it back here. Let's actually pull it out of the whole tensor. Okay. So all of these things are equal in the tensor product. Yeah.
All right, so we can pull the 2 out of the whole tensor. We can put it in right behind this set of parentheses.
Mm-hmm.
And then we can also pull it right behind the scalar. I mean the matrix, right?
Mm-hmm.
Just keep it anywhere we want there. Something like that.
Yeah, it's just the third line on the relations, right?
So I used every single one of the, well, maybe I didn't use this one. But I used this one and this one and this one.
Because 1 is in the field, is it ever okay notationally to drop 1 with the tensor product?
You don't want to drop this 1. You want to have something there because you need an element of v here, and the element of v is going to be
Just to remind you
1.
that you're in that.
Yeah. Yeah. So let's do one more thing, and I mean, you see there's a lot of things you could do, and we could spend hours doing this, but let's just do one last one that we haven't done. And I think I know what you mean. One thing that I can do is split this like this. Yeah. And I could actually decide to pull out this minus sign and into here. So these are all the kinds of things that you can do. And those are the kinds of operations you're allowed in the tensor product. Okay? Yep?
So just looking at the relations for the tensor product and comparing those for the like cross gratifying product.
The direct product.
Direct product, there we go. Can you see why the dimension, just by looking at the relations, why the dimension of the tensor product is n times n versus n plus n for the other one? I think it's obvious.
So the question is how can from these relations how can you see that dimension of V tensor W is dimension of V times dimension W? I don't think it's obvious, but I think it's provable given what I've told you, and that's precisely what this exercise is. And I should say that in this class we actually have a place for these exercises to go. So the things that are not homework problems that I just say like, oh, this is a fun exercise, these are great things to put in the discussion forum. And if you follow this discussion forum and if we settle these fine points, then I think you're going to be in really good shape to really understand exactly what's going on. So I want to defer that discussion to the forum. I'm not saying it's obvious, but I'm saying it's provable given what I've given. Okay, so let me just do one other quick example of this so that you know how it works, because sometimes it's going to get a little bit more confusing. What if U and V are the same thing? Okay. Then I can do something like I can consider, for example, 1 plus 2x tensor x minus 2x squared. Okay? And, well, this is a tensor product, so we have a formal multiplication of these things. So what is this equal to? Well, you're tempted to distribute this, I hope. Can I distribute it? Can I hate this FOIL, but so you know what FOIL is when you distribute A plus B times C plus D. Okay. Can you do FOIL? You can do FOIL. You can do that because tensor product is distributed both on the left and on the right. So you can do 1 tensor x plus 2 x tensor x. Maybe I'm not doing it in the order that FOIL prescribes, but you know that it's okay no matter what the order is, right? Minus 1 tensor 2x squared minus 2x tensor 2x squared. Okay? And you start seeing these things are a little bit hard to read. Maybe if I parenthesize them, it'll be a little bit nicer. Now, where should I put the parentheses here? Actually, I just kind of want to put it here. And it doesn't matter where I put it because the scalar, I can put it in or out of the thing. What else should I do to simplify this? Yeah?
Okay, so here, are you saying, just one thing, sorry. I mean here, so the addition in here is then commutative and essentially.
Addition is commutative because this is a vector space. Yeah. Whenever we write addition, it's always commutative. Yeah?
On that last term, you can pull out a 2.
I can pull out a 2, and I can actually pull out another 2, and I can make it a 4. Okay, so let me take this, take it into a 4. This is very careful operations. And what should I do here? Well, I can pull out the 2, and I get minus 2 times this.
So these parentheses then are more for eliminating confusion, right? Because you can pull these scalars in and out wherever, and it doesn't really
I'm putting parentheses so you can read, because otherwise it's hard to know what this expression is. What is the next thing you want to do? We're simplifying this thing, right? What is the next thing you want to do? I hope somebody's tempted to do this, even if you don't know if it's legal or not. I mean, if this was, if you didn't have the tensor product there, if there was the normal product,
Can we
They call x point x,
get the
x
x
squared.
style?
if this was the normal product, you would want to cancel out this guy and this guy because they're both 2x squared. So the question now is, can I cancel out this guy and this guy? Yes or no? No, because what would it mean to say that x tensor x equals 1 tensor x squared? That would mean you're pulling out an x from here and bringing it into here. So let me again write a warning sign here. X tensor x is not the same thing as 1 tensor x squared. Because you cannot pull out an x from here and put it into here. You can only pull out constants.
You can group the x squared things together once again, like 1 and x.
The point that I want to make is just that you cannot cancel these things as you might be tempted to. And in that way, you'll see that whereas in the previous example, we had the extra freedom of multiplying things, here we're actually losing freedom because we had a multiplication that worked beautifully, and now I'm telling you cannot really use it as you're used to. Yeah, this is a more restrictive kind of multiplication where you cannot cancel this and this. Okay? And so this just doesn't cancel any further. I mean, you could do other things, move things around, but you cannot cancel this term and this term. Okay. Any other questions about this?
Would we want to keep it simplified like that, or would it be easier to group things and other things together?
It might be that you want to group things differently. Actually, that goes to the next questions that I wanted to say. So let me give you another warning, which is that not every element of V tensor W is what's called a pure tensor. Little v tensor little w. There are elements in here that you cannot write as something times something, something tensor something. You have to write them as combinations. And I want to see an example of this. So this is another exercise that I'm going to give to you. Find an example of something that is not a pure tensor. Okay? And let me give you a green question. This is not something to worry about, but something to explore. So the question, what is Rx tensor Rx? Is there a simpler way of describing that? And again, that'll be a question to discuss in the forum. Is there some simpler way of denoting all of this stuff? Okay. So I hope that gives you a better idea of how tensor products work. Now, let's go to actual examples, because I was talking about some motivating examples, but I'm promising you connections with a lot of things, and we haven't really seen any of those connections yet. So let me erase all this stuff. And now, we're going to see at least 4 examples of Hopf algebras. So first example is coming from groups. Okay. I'm realizing that there's one more thing that I wanted to say, which is that. So let me say it here. If you also have that V and W are rings, like they were in this example that I just erased. Right? Both V and W were the polynomial ring. Then you can actually make V tensor W into a ring if you multiply. So this is implicit in what I was just saying. I'm just making explicit something that we were using a moment ago. We were actually multiplying these tensors with each other. Right? We did FOIL, we multiplied these tensors. How did we do it? We actually did the multiplication component-wise. Were we justified to do that? Does this expression make sense? Well, if V is a ring, then you can multiply elements of V. And if W is a ring, you can multiply elements of W. And so this gives you a proper multiplication rule for the tensor product. Okay. That means in the previous example that I just erased, we actually were multiplying things, and this is the way we were doing it. Okay. Okay. So let's do some examples. Let's say that we start with a group. Okay. Now, one thing that you'll see about Hopf algebras is that they're a vector space, but they're also a ring. Okay. And so we want to build a Hopf algebra out of a group. Should be a vector space, should be a ring. Now, is a group a vector space? Not really, right? A group just has rules for multiplying elements in the group according to some axioms, but you don't have a way of adding or multiplying by scalars. But do you remember how we turned it into a vector space? What we did is that we introduced a field, and we defined something called the group ring. The group ring is given by just linear combinations of group elements. Linear combinations of group elements. The lambda i's are scalars. The gi's are in the group. Okay. So this is a vector space, right? Because we're looking at all the possible combinations of group elements, and so those things can be added, and they can be multiplied by scalars. Okay? You can add expressions of this form, and you're going to get an expression of this form. And if you multiply an expression of this form by a scalar, you get an expression like this. Now, I'm calling this a ring. So do you remember what the multiplication was here? How do you multiply things like this? You basically kind of distribute and the scalars go together and the group elements are multiplied in the group. So let me say it like this. The multiplication in the group ring is equal to the multiplication in the ring, in the group, I'm sorry. And we extend linearly. Okay, and what I mean by that is that if you if you want to multiply this and this, so another element looks like this. Then you just kind of distribute. Sorry, this is mu j. So you sum over I and j, lambda I, mu j, and then gi hj, where, because the gi's and the hj's are group elements, we multiply them in the group. Okay? So this gives us a multiplication. Okay? And that's good because that means we're partway through defining a Hopf algebra. We have a vector space with a notion of multiplication. Now, it also has a co-multiplication. So I'll erase this stuff. So what is a co-multiplication? A co-multiplication is supposed to take an element of H and take it to a tensor or something in the tensor product. Okay? So I need to define for each element of H, for each element in this group ring, a coproduct, okay? Now, in particular, so I need to define delta of anything of this form. So let me define delta of a group element. How should this look? It needs to be something that lives in the tensor product, right? The tensor product of this and this with itself. Let me ask you to, what is, I don't know, what would you try? You could say that it's one tensor G. That could be a possible definition. What do you like about one tensor G? It's nice and easy. Right? That's why I like it. What don't you like about one tensor G? It's not symmetric. It's asymmetric. Maybe that's not a big deal, but can you think of something simple and symmetric? G tensor G. It turns out that if you go for the simplest thing, which is this, I mean, you don't get to just do this at random. You saw that there's a whole list of rules that these things need to satisfy, and one tensor G is a great guess, but when you go to check the rules, you'll see that they're not satisfied. But if you define the kind of next simplest thing and the nice symmetric thing, then this turns out to satisfy all the axioms of a Hopf algebra.
But it's not linear, is it? Only, okay, maybe, okay, tensors. I was thinking of one tensor G plus G tensor 1.
Okay, so another good choice could have been one tensor G plus G tensor 1. And,
but the question of linearity, I guess with tensor, you need to talk about that, right?
That's absolutely right. So you see so far I've defined the coproduct of one of the generators here. But now I need to tell you how to take the tensor of a sum. So for example, another so what happens if you do this? Okay. Well, delta is, this is not just a map, it's actually a homomorphism. And so if you have something linear here, it should translate to something linear there. Okay. And so by linearity, you can see what this needs to be. Okay. And I think it's a good exercise for you to do that. So you should see, given this, what does this coproduct need to be? And it needs to be something, and that is what it is. Yep.
Despite what that clock might be saying, there's 4 minutes left until 10:50 in the real world.
Okay. Thank you. Yep.
Okay, so here, this go like. Okay, so say we have a tensor product of two things, right? So say M1 tensor product N1 and M2 tensor product N2. Under what conditions are these two things equal? And so, I mean, what I'm trying to say is like, how do we know this thing is actually well defined?
Great questions that we'll see the answers to. And it's not easy. It's not easy if I give you something tensor something and something tensor something. Do you know if they're equal?
Yeah,
It's not obvious. Okay. Let me just say this multiplication and co-multiplication do give a Hopf algebra. Okay. So from a group, you build a Hopf algebra like this, and then you can use Hopf algebraic techniques to study your group. Okay. Next time, we will do the same thing for polynomial rings. So in polynomial rings, you can think about how do you define multiplication and a co-multiplication. Or with graphs, how do you multiply graphs and co-multiply graphs? Or with permutations, how do you multiply two permutations and co-multiply two permutations? We'll see that there's good ways of doing this. And then that'll motivate why it is that we want to deal with these kinds of objects. Okay? Okay. So I think let's stop the mathematics now, and let's take a vote on when the office hours should be. So they need to be either Tuesday or Thursday, and they need to be either at 11, at 12, at 1, or at 2. Okay? When is homework going to be due? Let's either on Tuesdays or on Thursdays. Let's choose the office hours, and then we'll choose when homework is due. Okay? Should we do that, or let me? Wait, I think I actually said what day is February 7th? Can somebody tell me?
Tuesday.
Homework due Tuesdays. Yeah, actually, I have I need to make it on Tuesday so that it matches Columbia. So you get as many votes as you want. Okay, but then voting is kind of funny. So we're gonna choose two. We're gonna choose 2 hours. And well, let's just take a vote and see what happens. Okay, so you can vote as many times as you want, but lift your hands high and make sure that I count you. So who wants this hour? So that's right after class 1. 8 people. Who wants this hour? 4. Who wants this hour? 5. This one? 1, 2, 3, 4, 5, 6, 7, 8, 9. This one? 3. Okay, let's see what's going to happen now. 4, 8, 12 people. This one? 7 people. This one? 5, 6 people. And this one? 2, 5, 6, 7, 8, 10, 11, 12. Okay. Now, let me ask you something. Can everybody make 11 o'clock? Can everybody make 2 o'clock? Can everybody make either 11 or 2? Okay. And we're going to have to sort something out, but I guess...
It would be to pick one of those two and then have everybody who can't make them vote a second time.
Since this is a tie, I'm going to break it, and I'm going to choose this. And let's...